First, thank you. First, I would like to do a little of history. The value of the group started when Jaime Dominguez visited the NIT, invited by Professor Suresh at the middle of the night. During this visit, he developed and constructed a fretting fatigue apparatus for testing. Here we can see a picture of a similar apparatus, but there is very constructed in Seville at the beginning of the 2000s. The main characteristic of this apparatus, in contrast with the frequently used fretting ring, is that with this apparatus you are able to apply independently the three major fretting loads: the normal load, the tangential load, and also the asphalte. This can be done moving these clampings. Sorry, it doesn't work. Much better. Okay. And so the use of this type of machine is very flexible. Actually, Jaime is an emeritus professor, and although he is still working on research, the most active part of the fretting group is formed by my colleagues Carlos Navarro, Diego Arena, María Moreno, Vicente Martí, and also me. Okay. After this very brief explanation of the history of the group, I'm going to present the most outstanding research done by the group on the fretting fatigue field. First, I would like to introduce the problem of fretting. Fretting has the characteristic that has an extremely steep stress gradient below the surface. For this reason, palliatives like shock, laser pinning, coatings, treating, rising, extruding, and also lubricants acts as a very good palliative against fretting. It's also important to know that in many practical situations, this very steep stress gradient is reduced in less than 100 microns. For this reason, in the group, we have worked a lot with palliatives against fretting. The first palliative studied against fretting was coatings. In this case, molybdenum-based and Teflon-based coatings. In this picture, we can see a resume of the test done with this type of coatings. Here, we can see the fretting fatigue line obtained as a function of the bulk stress applied to the test specimen, and also as a function of the tangential load applied. The first thing that we saw in this test is that independent of the fretting regime, the deterred coating always produces a bad result when compared with the uncoating cases. Also, saw that in the case of molybdenum-based coatings, the behavior was good. We observed a good behavior only when the tangential load was low, and also in the high cycle fatigue regime. Okay, we also observed that in both cases, the coefficient of friction is lower than in the case as machine. And we observed that the bad behavior produced with the tooth was due to a premature breaking of the coating. We also had an important effort in order to understand the behavior produced by shock and laser pinning. Perhaps the first thing that comes to your head when you think in shock and laser pinning is the residual stress and also maybe the work harmony, because this is the main feature that produces the handling in the plane fatigue case. But an important thing is that in fretting, the contact surface condition matters. Here, we can see some pictures, some confocal image, confocal perspective image in different conditions. In the mass machine test specimen, with the shock test specimen, and with laser period. Also, we can see the different fretting scar obtained in each case. After so that we thought that maybe this surface condition and the different fretting scar obtained has an important influence on the fretting behavior. To deepen analyze this behavior, we did some fretting tests. Here in this plot, it's shown the fretting fatigue lies as a function of the fretting load and for different surface conditions. First, we have the baseline. Those tests done with as machine fretting fatigue test specimen. Then we have those tests done with laser and shock period test specimen. And finally, we did some special tests in which the surface were minimally machined, just only to remove the characteristic surface produced by shock and laser beam. We can see the important effect produced by the surface condition on the fretting fatigue, especially in the shock beam test specimen. In order to deepen into the effect produced by the shock period characteristic surface condition, we need some special tests. In this test, the fretting specimen were as machine, but the contact paths were shock period. Here, we can see that we did fretting tests in spherical contact and also in cylindrical contact. We observed that at the high cycle fatigue regime, the behavior was very good due to the surface firmness. In both cases, in spherical contact and also in cylindrical contact. But we also observed in contrast that at lower lies, the behavior is also clear. So with this test, we observed the importance of the surface condition in fretting fatigue, not only residual addresses. In order to analyze these results, we did some numerical models. In this case, with this known model, we introduced the characteristic shock beam surface condition in the back. And we analyzed what happened on the surface and with the surface. Here we can observe the Smith-Wasson-Chopper distribution and also the stress intensity factor mode 1 along a line starting from the most damaging point of the contact surface, the hot spot, and perpendicular to the contact surface. We can observe the following. Very close to the surface, that cases having the typical surface roughness of shock pinning produce higher values when compared with the smooth cases. But below the surface, the important thing here is that below the surface, we can observe an important decrease of the Wasson-Chopper parameter or the mode 1 stress intensity factor is produced. So this result can explain why the characteristic surface roughness produced by shock pinning can be used as a palliative against fretting. We also have worked a lot with other types of palliatives. This palliative can be considered as geometrically based palliative. Also, this type of palliative can be considered as counterintuitive. Especially, the palliative consists in introducing points below the surface. Here we consider the result obtained in a cylindrical contact, introducing a circular void. In this case, the important thing is that when you introduce this void, an important redistribution of the contact surface stresses is produced. Due to that, an important decrease of the contrast stress field below the surface is produced. And here we can see, for example, some results. In this plot, we can see the mean value of the Smith-Wasson-Torre parameter along a line perpendicular, along a line with different angles, starting from the most damaging point, the hotspot point. We can see that in contrast with the no-void case, when you introduce the void and depending on the geometry, we can observe an important decrease of the mean value of the Smith-Wasson-Torre parameter along this line. Also, we have worked with more industrial application. In this case, we have worked with the press-fitted shaft half connection. In this case, we introduce a toroidal void in the shaft. Here, in this plot, we can see the direct stress on the surface, just along this line. And we can see that when compared with the no-void case, and for a certain geometry below the surface, you can, just at the surface, you can observe an important decrease of the direct stress. So it's expected that this type of palliative can work very well. Also, we have worked with another type of geometry-based palliative. In this case, we have worked with wavy surface. But in this type of wavy surface, we try to resemble the waviness produced by shock pinning in the surface. We analyze two cases. The first case is the waviness is introduced in the test specimen, and in the second case, the waviness is introduced in the bath. Here we can see similar result that I have shown before with the surface removed due to shock pinning. We can observe here for the fatigue parameter along a line again starting from the hot spot. You can observe that very close to the surface, the values are higher than compared with the smooth cases. But also we can observe that below the surface, a substantial decrease of the value are produced. So a good behavior is expected with this kind of waviness. Also, we analyze the mode 1 stress intensity factor in that case. It's important to know that when you introduce the waviness in the test specimen, always the mode 1 stress intensity factor is lower than that obtained with the smooth case. On the other hand, we have work in the development of a reliable and with physical sense fretting fatigue model. Also, with a fatigue model that uses a non-arbitrary crack initiation length. For us, there are two important questions that are not fully resolved nowadays. The first question is how to determine the crack initiation length. And the second question is how to obtain the crack initiation length. In order to solve this question, we have developed and continually modifying our fretting fatigue model. Here, there is a very brief explanation, a simplified explanation of the model. First, you need to obtain a hot spot at the contact surface. Then it is assumed that the crack initiates and propagates along a line starting from this hot spot. For the time being, we assume that this line is perpendicular to the contact surface. For a certain crack initiation length, you can obtain the number of cycles required to initiate it. Then, using fracture mechanics procedure, you can obtain the number of cycles required to propagate that initiate crack until the final fracture. Adding these two fatigue life, you can obtain the total fatigue life for this assumed crack initiation length. You can repeat the procedure for different crack initiation lengths, and thus obtaining a fatigue curve that gives you the total number of cycles as a function of the assumed crack initiation length. From all the possibilities, we consider that crack initiation length giving the minimum total life. And this is the crack initiation length, and this is the total fatigue life specimen. This model has been applied very good results in many situations. For example, components having a stress gradient, not only fretting, cases having 3D pressure, like elliptical or semi-elliptical cracks, situation having residual stress, also including its relaxation, and self-steel cracks. For me, special mention, it is required for the last case, when the cracks are self-steel. In that situation, in both phases, in the crack initiation and in the crack propagation phases, the cracks dictated by the model are self-steel. This model produced very good results in terms of the fatigue life predicted, but also are very important in terms of the crack predicted. We can see here the experimental crack path, and we can see here the different crack path prediction by the model. Lastly, but not less, we have moved to the fretting fatigue at high temperature, working with supralloy Inconel 718. We have obtained very good results and very nice results, but I need to say that I don't want to do a spoiler, because yes, after me, my colleague, Mario Moreno, is going to do a very, very nice presentation, likely better than mine. So, so I am very happy to announce that. Okay. Thank you very much for your attention. I will be very happy to respond to your questions. Okay.